Continuing our discussion of reactions at the alpha position, now let's move on to discussing a different reaction, halogenation. If I have a ketone or an aldehyde, I can treat this with bromine in the presence of an acid catalyst to form an alpha-haloketone or alpha-haloaldehyde. These compounds are useful for other synthetic transformations, which we'll discuss a bit towards the end of the video. Show a mechanism for this reaction. So note a few things before you start. First, this reaction is not going to go through an enolate intermediate, it will be through an enol intermediate. The way we know that is that this reaction is happening under acidic conditions, so we are not permitted to form strongly basic intermediates. Since we're making an enol, the nucleophile for this reaction will be that enol, the electrophile will be bromine. Note that this is not a free radical reaction, so double-headed arrows please. Third, be careful to watch your proton transfers. Don't accidentally make any strongly basic intermediates, and be careful about transferring protons when you need to. Take a minute and try to work through this, and then we'll discuss the mechanism together. Unsurprisingly, the way we start this reaction is by protonating the carbonyl group of our ketone. This gives us this oxonium ion as the intermediate. Now that we've protonated the carbonyl group, a weak base like water can remove the alpha proton, generating the enol as our reactive intermediate. This enol is a nucleophile. It will react with bromine as an electrophile. The electrons will come back down and will pick up a bromine at the alpha carbon, regenerating an oxonium ion. This oxonium ion is a strong acid and will be deprotonated by our solvent in this reaction, which is water, to form our alpha-haloketone and regenerate H3O+. If you look carefully at this reaction, you might notice that this reaction actually produces one extra equivalent of H3O+. This type of reaction is often called autocatalytic because the reaction actually produces an excess amount of the catalyst that it's requiring for reactivity. How about the selectivity of this reaction? If we have an asymmetric ketone, like 2-methylcyclohexanone, and we do this reaction, we could get two different alpha-halogenation products. In these reactions, the major product is always the one that is formed from the more stable enol. This reaction works with chlorine, bromine, or iodine, and the mechanism that we drew in the previous slide is supported by the fact that the selectivity is not significantly different no matter which halogen we choose. The rate-limiting step of this reaction is enol formation, which means that the dynamic enol is the control for the major product of the reaction. In these reactions, mixtures are unavoidable, but the thermodynamic enolate will determine the major product. So let's take this as an example. What are the products that you would form, and what's the major product of the reaction? Work through this, then restart the video and we'll check the work. So here the major product would be halogenation at the more substituted carbon because that's where we would get the more stable enolate. It's possible to do reactions with these afterwards. For example, these can be treated with pyridine to generate alpha-beta unsaturated carbonyl groups. We'll see these later as interesting electrophiles for a variety of reactions. There is a special case of this reaction which is known as the Hell-Volhard-Zelinsky reaction. One fact that we'll need to know as we continue to go through this chapter is that esters, amides, and carboxylic acids really do not form enols readily. So that means that if we want to take a carboxylic acid like this and brominate it at the alpha position, we need slightly different reaction conditions to overcome this problem. So in this reaction, we're treating our carboxylic acid with bromine and PBr3 in a first step, and then water in a second step. So to go through this reaction step by step, first our carboxylic acid will react with PBr3. We saw a similar reaction to this back in Chem 2131, so it shouldn't be a surprise that we're making an acyl bromide here. After we make the acyl bromide, it's possible for this to start equilibrating with the acyl bromide enol. This enol forms in large enough amounts that if we treat it with bromine, we'll get halogenation at the alpha position. After we've done this, treatment of the acyl bromide with water will cause it to rapidly hydrolyze, regenerating the carboxylic acid. Interestingly, this reaction will also work under basic conditions that favor enolate reactions over enol reactions, and it will favor polyhalogenation. If I take a ketone like this, and I treat it with bromine in the presence of a base, The interesting thing about this reaction is that all my alpha hydrogens are going to be replaced with halogens. In this case, the left side of this ketone does not have hydrogens and will not react. The right side has 2 protons, and we will end up forming a dihalide. So this reaction proceeds initially like we would expect. A ketone plus a base will form an enolate. This enolate is a nucleophile, and it will react with bromine S, an electrophile, to form an alpha-haloketone. Now, if we look more closely at this, we'd say that the pK of this proton is probably somewhere in the range of 16 to 18. No matter what that pK is, the compound that we get as a product is going to be more acidic than the compound that we started with due to the inductive effect of the halogen. So then, the second equivalent of base will heavily favor removal of the proton of our halogenated compound over our starting material, which means that the second enol is more favorable, which means that the second halogenation is going to be much faster. So no matter what we do here, even if we're very careful about stoichiometrically restricting the amount of bromine that we have, we'll favor the formation of the dihalogenated product over the monohalogenated product. If we do this with a methyl ketone, like for example acetophenone, the reaction that occurs is known as the haloform reaction. Under these conditions, we get these 2 products, a carboxylic acid and a haloform, HCX3. If those halogens are chlorine, we would call it chloroform. If they're bromine, we would call it bromoform. So that's where that word comes from. So the way this reaction works is that at first we get the expected polyhalogenation reaction. We replace one hydrogen with a halogen, and then the second hydrogen with a halogen, and then the third hydrogen with a halogen to form this trihalocarbonyl group here. Now, if we look at this, we can see that those 3 halogens are going to be exerting a fairly powerful inductive effect, which makes the carbonyl group of this ketone exceptionally electrophilic. So under these conditions, water will rapidly add to generate this tetrahedral intermediate. This intermediate will then collapse, kicking out CX3 as a leaving group. Now I'm going to take a moment here because I can hear what you're thinking. You're thinking, is this really acyl substitution? We're kicking out a carbon as a leaving group? Well, we're not just kicking out any carbon as a leaving group. CX3- is actually pretty stable due to that strong inductive effect from the halogens. Also remember that in acyl substitution, the leaving group leaving is not the rate-limiting step, so having a bad leaving group is not a killer for this reaction like it would be for E2. This compound is still pretty basic, so it'll remove the proton from our acid, giving us a carboxylate anion and HCX3. This is why we need H3O+ after the reaction occurs to reprotonate the carbonyl group and give us a neutral product. Let's do a little practice with this. So, part 1, how could you adapt these processes to make alpha-halo esters? Try to come up with a reaction or a sequence of reactions that would give you an alpha-halo ester, then come back and we'll discuss some of the ways to do this. Probably the easiest way to convert a carboxylic acid directly into an alpha-halo ester would be via the Hell-Volhard-Zelinsky reaction. In this case, since we want a chlorine added to the alpha position, we would need to use Cl2, and we can use thionyl chloride to make the acid chloride. Once we have the alpha-halogenated acid chloride, we can simply treat it with ethanol to make the ester. Why would we want to make these, you ask? Well, because if we add triphenylphosphine to these, followed by a base, this is how we make the stabilized Wittig reagents for the Wittig reaction. This is a very easy way to make an unsaturated ester. For a second problem, I want to look at the synthesis of hexachloroacetone. If you take acetone and treat it with a large excess of chlorine with an organic base pyridine, you can make hexachloroacetone, which is a useful reagent for making some interesting pesticides. So in this reaction, the question I'd like to answer here is, why did I use pyridine rather than sodium hydroxide? Try to come up with an answer for that, and then come back and we'll check your work. The reason why we don't use sodium hydroxide for this reaction is if we do, we would favor the haloform reaction, generating the acetate anion and chloroform. Now, one additional question to answer is if we do the haloform reaction here, Why is it that my acetate ion ends up with no halogens on it? So try to work through this reaction, and I'll leave that as a question that we can answer during lecture. Next, we'll take a look at some very versatile carbon-carbon bond-forming reactions, starting with aldol addition and aldol condensation.